Hello and welcome to Feature Engineering, Dimensionality Reduction, Feature Selection and Feature Extraction. This is part 1 of video 1. So we'll be having 3 parts for this video. In this part 1, we'll be primarily defining the term dimensionality and dimensionality reduction and 2 of its types, feature selection and feature extraction. We will also be focusing on the fact that the problem in general settings is really ill-posed and very complicated. In technical terms, the problem is really called NP-hard. But then we will see in most of realistic settings, certain assumptions really hold, and a lot of fancy algorithms that are there to actually help out carrying out this dimensionality reduction. So let's start by defining dimensionality reduction. What does it mean? Before basically defining dimensionality reduction, we should first define the dimensionality. What is dimensionality? You might have heard this term a lot many times, dimensionality of the data, then dimensionality of the data. Let me define what do we mean by dimensionality. And let me define this in terms of an example. Assume that your task is to find out so your task is to find out whether a particular person has a particular disease or not. Let's say the particular person has disease of type A or not. That's your task. Now you want to build an automatic system that basically tries to find out that a person has disease of type A or not. And now you're thinking about the attributes that actually are helpful in categorizing whether the person has this disease or not. So maybe the demand of this disease to be categorized, maybe one attribute is weight of a person. That might be one attribute, or we call it one feature. It may be helpful in categorizing that a person has disease A or not. Another feature might be an age. That might be a feature. Age. We may have blood cell counts, different blood cells, for example, white blood cells and red blood cells. What are their counts and ratios? These maybe are the features, maybe more than one features, but a feature. Let's say blood cell count. White blood cell count is one feature, red blood cell count is another feature, for example. And we may have many more features. And our goal is to utilize the information contained in these features to categorize whether a person has disease A or not. Well, all these features, if you categorize one person, so let's say this is person 1, the weight value, let's say person 1, the weight value we have, that's weight value, let's say that's age value, that's red blood cell count, that's white blood cell count, so WBC, red RBC. If we define like a table like so, then for person 1, the weight value might be in certain units. The weight value might be, let's say, 50. The age might be, let's say, in years, or might be, let's say, 45. The RBC in certain units are, let's say, 2, and WBC in certain units are, let's say, 3.1. So then we may have another person, for example, person 2, with different values of these features. Maybe the person 2 has weight 65, age might be 31, RBC value might be 1.4 in certain units, and WBC value might be maybe 2.9. And then we can have several persons and their data. This data, the number of features that we are basically carrying out to categorize this particular disease, these number of features, that is called dimensionality of the data. In this particular case, the dimensionality of the data is 4 because these are 4 features we are working on. We are basically, based on these 4 features, we are going to decide the type of the disease. In other cases, for example, this dimensionality of the data is really high, maybe very, very high. For example, let me give you an example. Let's say you have an image. Let's say you have an image. Image is a matrix. Normally, a matrix. Let's say it's a grayscale image, so we don't care about the RGB channels. It's a matrix, and let's say the image is really. In this particular case, I'm going to take the example of the image, which is just 4x4 image. And let's say our goal is to build a face recognition app. Let's say we are going to build a face recognition app, and we have a lot of face images of several people. Now, this pixel, which is at position 1 and 1, the value in this pixel is any value between 0 and 255. These are the grayscale. So this can be any value between 0 and 255. And then 1, 2, that is any value between 0 to 255. This is any value between 0 to 255, and so on. Now, each cell in this matrix is a feature. For example, this might be first feature, this might be second feature, this is third, this is 4, this is 5th, 6th, 7th, 8th. In this particular case, we have 16 features. And based on these 16 features, we are going to decide who the person is this, having this face image. Now, in real settings, these images are no longer 4x4. They are really high number of pixels in those images, and it is not uncommon to have features, to have images like 1000 by 1000 or something like so in these days. So in this particular case, the total number of features that we are working on is 10 raised power 6, which means the dimensionality of our face recognition data, the total dimensionality of the data is 10 raised power 6, which is really high. Now think about RGB images where we have 3 channels, R channel, red channel, and red channel, green channel, and blue channel. So we will be having 3 images, each with dimensions 1000 by 1000, which means the dimensionality of our data now in RGB case is 3 times 10 raised power 6. Very high dimensions, very high dimensions. Now think about videos, for example. A video is just a sequence of a lot of images. So in that sequence, we will be having a lot of images. So another image, and so on. So for example, if we have a camera that is, let's say, that work on 10 FPS, where F means frames or images, P means per, S means seconds. So if the camera captures 10 images per second or 10 frames per second, then and now we have an image. Now we have a video clip, for example, of 40 seconds. So what do you think? How many pixels are there in a video of a 40-second clip captured by a camera with 10 FPS, 10 images per second? Well, assuming the image dimensionality or the image dimensions are 1000 by 1000, and assuming the RGB image for 1 second, we have 10 images. So each image has this dimensionality, but now we have captured the video clip for 40 images. So you can calculate this number, and that's dimensionality of the data. So in real situations, the dimensionality of the data is really, really high. So dimensionality of the data means the total number of attributes or the features of the data we are working in. The data might be assumed for a classification task. It may be assumed for a regression task. It may be assumed for a clustering or grouping task or any other machine learning task. But the dimensionality at the end of the day is the total number of attributes in one record. in what data sample. So that's what dimensionality is. So I have given you example of, for example, this is an example with only 4. The dimensionality of the data is 4 here. The dimensionality of the data for this kind of data set is 16, which is fine, but the dimensionality of this video data with this kind of case is huge. Now, the problem is, what is the problem with a lot of dimensions? If we have a lot of dimensions in the data, if the dimensionality of the data is high, what is the problem with that? Well, there are a lot of problems. Let me first define some of the problems that are related to computational complexity. One is obviously the storage. That is one problem. So you need a lot of storage to store actually a lot of data if the dimensionality of the data is high. Second problem is the computational time. Computational time. So if you're going to fit certain models, some computational models, machine learning models, on the data with high dimensions, the models, they tend to consume much more time to complete than otherwise. But I will not be actually discussing a lot these two properties, because maybe increasing hardware, or maybe maybe hardware can capture the storage issue. Maybe the hardware or the parallel computation kind of setups, they may one way or the other, or to some extent, may capture efficiency in the computational time. The bigger bottleneck that the higher dimensionality brings in is overfitting. That's a bigger bottleneck. The more dimensionality of your data, the model you're going to fit tend to have many more parameters. And one way to define complexity of the model, that the model is how much the model is complex, how much the model is flexible, machine learning model. One way to describe the complexity of the model is the number of parameters of that model. Number of parameters. So more number of parameters means more complex model, more flexible model, means high chance to overfitting. And overfitting means whatever model you, in a very casual way, overfitting means whatever model you came up with, it will tend to not generalize very well on the unseen data or the test data or true test data. So you may come up with a model that performs very well on the available data, but once you deploy that model in the real setting, the upcoming data that were never used in the training process of any machine learning model, on that data, which is called the true test data, the model may not perform very well, which means the model just overfit on the available data and is useless. Basically, that model is useless if it is not going to work on the unseen data or the data that appears after the deployment of the model. And that's the main issue. I mean, that's the very kind of, these issues are there. I mean, I'm not saying these are not the, but these issues are trivial, maybe trivial in several cases where the hardware is available, but this issue is no longer trivial. This is not an issue that is avoidable, but this is not an issue that should be thought of as very minor kind of issue. Overfitting is a huge issue. And if you have high dimensional data, you're going to fit, even you might be thinking a very simpler model on high dimensional data, but even with a very simple model on high dimensional data will be containing a lot of parameters, and the problem of overfitting is there, which means no matter what model you come up with, the chances are that it will not perform very well on unseen data. Those chances are high if your dimensionality of the data is high as compared to the number of data points. You can reduce the overfitting by keeping the dimensionality high by sampling more and more data. If you have more and more data, then the high dimensionality of the data may not cause overfitting, but the high dimensionality of the data actually brings very large demand of the training data to avoid overfitting, which in most of the cases is not feasible because data collection and having a lot of data to avoid overfitting in several cases is much more expensive. So dimensionality reduction is required because one, storage, that's okay, we can deal with that with hardware, maybe to some extent. Two, computational time is there. Okay, we might be going to cloud computation and we might be availing certain hardware services, fancy hardware services, parallel computation and stuff like so. So we may be taking care of computational time to some extent as well. But the problem is overfitting is not minor. This is the problem that we have to face if you're going to build any machine learning model on the data with high dimensions. So yeah, so we need to reduce the dimensionality to improve our storage, to improve our computational time, and primarily to improve our model generalization to decrease the overfitting. So that's the motivation. We need to reduce the dimensionality in several cases. If not in all the cases, in several cases, we really need to reduce the dimensionality. Now, there are several ways of reducing the dimensionality. If I just think of as the data to have a lot of dimensions or attributes, let's say x1 is attribute 1, x2 is attribute 2, x3 is attribute 3, and let's say we have d attributes of our data, and we have several records. So that, let's say that's the value of x1 of record 1, this is the value of feature 2 or attribute 2, that's a value, some real values or categorical values or whatever values are these. This is record 1, or this is data sample 1, this sometimes called sample point. That is data 2 or data sample 2, and let's say we have a lot of data samples here. Yeah, so yeah, so these. So now x1 is our feature 1, x2 is our feature 2, x3 is our feature 2, and let's say we have d features, and these are so this is the value of feature 1 in data sample 1, this is value of feature 1 in sample 2, and this is value of feature 1 in sample, let's say n, if we have n samples, 1, 2, and dot 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 n samples. Now, feature selection is a technique to somehow select a subset of the features from the available features, and even after the subset selection, the new subset has almost the same information. So the goal really is to come up with a subset of the features. Maybe we pick x1, maybe we pick x3, maybe we pick x7, maybe a subset of those. And even with those subsets, the information in that subset roughly is the same as the information in the whole set of features. Well, the information that we really want to gain, really want to preserve, might be the discriminant information. Which means the information that is required for classifying these records into certain categories. Let's say that is a class category. That is class category. Y is a class category. So the information, if this is a classification task, if really we want to use this data for classification, then the information we really want to retain is the discriminant information. What features are highly discriminative to describe the class, to discriminate among several classes? Maybe it's a binary classification problem. In that way, the sample 1 has class 1, the sample 2 has class 2, sample 3 has class 1, then so on. And so some of the samples, they go to category 1, some of the samples, they go to category 2. Let's say it's a binary classification data set. Then what subset of features, they are highly discriminative, that can discriminate samples of class 1 from the samples of class 2. Or the information might be the describing information, which means the subset of the features, they actually are as descriptive as the total number of features. So in several other terms, we call these as, sometimes we call these as reconstruction information, or the information that describe the whole sample. That is possible if a lot of these features are highly correlated to each other, or some of those are just truly redundant or stuff like so. So feature selection is a technique to select a subset of features out of all the features by keeping the information, by keeping the same amount of information, roughly the same amount of information. And the information might be keeping the discriminant information, or might be the whole description, or the describing information that can describe the data set. The other type of dimensionality reduction is feature extraction. Feature extraction, or let me call it as feature transformation. In this technique of dimensionality reduction, we don't really keep the original features, but we construct a new set of features. So for example, if you're given a lot of features, x1, x2, x3, ... xd, let's say we have d features, then we may come up with a new set of features, let's say y1, y2, y3, ... yk, where the goal really is, again, that k is really smaller than d. We construct new set of features from the original features, from the raw features, and the new set of features is really small. We need not to actually keep the original features as it is. We just construct some new features from the existing features, and the new features in number, they are smaller than the original features, and we now are going to work with these kind of features. Again, the construction actually has to take care of that the new set of features, they actually keep the same information. Sometimes this same information is to keep the geometry, or the submanifold structure or subspace structure of the original data, or geometry of the data. Sometimes this same information means the discriminant information that is there. And sometimes this information means the reconstruction power of the new features. If we really want to reconstruct the original features back from the reduced, or from a few features that we just constructed, we could do that. So these feature extraction process can be categorized into several schemes. Some of the feature extraction schemes are really take care of constructing new features to keep the discriminant information alive. Some of those actually take care of to keep the reconstruction information alive, and so on. But in feature selection, we keep the original features, we select some of those but to keep the same information. And in feature extraction, we construct new features to actually keep the same information. So these are two basically types of feature or types of dimensionality reduction in this particular paradigm. Now I come to the problem that this particular problem is really complicated. So let's take an example of feature selection. Feature selection, let's say we have x1, x2, x3, xd features, and we are going to select a subset of these features. That subset must fulfill certain criteria. So we have some criterion, whatever the spelling is. We have some criterion, maybe the information gain, maybe keeping the discriminant information, maybe what subset is going to be very good for classification, what subset is going to be very good for clustering, what subset out of these will keep the geometry of the, will preserve the geometry of the original dimensionality or the original space, and all these kind of. So we have to set some criterion, and then we go to find out some subset of these. The problem is to meet a particular criteria, there is no way to come up with a subset efficiently in general by not exploring all the subsets. So in general, the only way to get the best subset is to go through all the subsets. And going through all the subsets is really a 2 raised power d problem. I mean, we have exponential number of subsets. Which subset is really the best is really, there is no algorithm that guarantees that the algorithm will not explore all the subsets and still get the best subset meeting certain criterion in general. So this problem is really NP hard, very complicated problem, and we need to explore all the subsets to get the best subset. But in certain cases, if in certain specific cases, we can build certain algorithms that really guarantee some of the optimality criteria. So for example, certain greedy algorithms, forward selection algorithms, and backward elimination algorithms, or some embedded methods, or I mean, there are some workarounds, some approximations that work very well in certain real situations, but in general, mathematically, the problem is really complicated. So this is not a simple problem to select really the features. So in this particular video, we basically talk about what is dimensionality reduction, what are its types, what is dimensionality itself, and why the problem of feature selection, why the problem of reducing dimensions using feature selection is really complicated. And in the next video, in the next part of this video, the next part, which is part 2 of this particular video series, we will be describing the algorithms that actually are used to do feature selection. And those algorithms, although they cannot guarantee in general settings the optimal subset selection, but in several realistic situations, those algorithms, some of those are greedy algorithms, some of those are filter methods and wrapper and embedded methods. There are certain algorithms or methods that I will be describing in the next part of this video that work really well in several real situations. So yeah, hope to see you in the next part 2 of this video.